Hello, Chem students. This is going to be hopefully our third and final lecture of Chapter 9 on the substitution and elimination reactions. Let's take a look. Remember from our last lecture, we were looking at carbocations. Carbocations were flat at the C alpha carbon with an equal lobe on top and bottom, empty p orbital. And then we could have some C betas around that carbocation. It had to be secondary or tertiary to form. Those were the only two possibilities that we looked at. Okay, the only reactions we showed last time were the final reactions, which is add a nucleophile from top or bottom, and lose a C beta H from top or bottom. So this top or bottom attack in both of these cases leads to more possible reactions than just the SN2 and E2. Now there's a new possibility that we didn't introduce yet, and that was the rearrangement. So this is kind of a complication because it basically starts the problem all over again. So if I can make a better carbocation than this one by moving some group across to this carbon, then that's a very likely possibility, and that would start the whole problem over again. So we could add a nucleophile, lose a beta CH, or it might rearrange itself to another carbocation, and we would start the problem all over again. Okay, so this might seem not realistic, but in fact, you have a steroid in your body that does this 4 times before it gets to its final result. Okay, so the problem with carbocations is they're so unstable because the carbon's missing 2 electrons, and it can react in these 3 ways. Every time you see a carbocation, it will be these 3 ways, and the rearrangement doesn't solve the problem, it just moves it to a new spot. Okay, so rearrangements are a temporary solution. If you do a rearrangement, it's because you're making something equal stability or better stability, and then you just start thinking all over again, substitution or elimination. Those are the possibilities. So rearrangements are very competitive with those other possibilities. Add a nucleophile, lose a C beta H. In our course, we'll have 2 types of situations. You can either predict or you can explain. So if you predict, there's really no product, and you have to just sort of make a reasonable guess. And for those, we'll only look at secondary rearranging to tertiary and tertiary rearranging to tertiary, okay, for predictions. If you have to explain, you might also have to use a secondary going to a secondary carbocation. So here's a little problem to test ourselves out on. Okay, we'll assume we have SN1 E1 conditions. So we have some neutral nucleophile like water or an alcohol. We come over here, we see secondary bromoalkane. The bromide leaves, and that leaves us behind a secondary carbocation, which is allowed in our course. Now for a rearrangement, we have to look at the C betas attached to that for groups that could migrate over and make something better. So if I come over and look at this carbon, we can show that over here. Okay, if I migrate a hydride over, that would leave us with a primary carbocation. That's not going to happen. We don't even propose primary carbocation, so this would be way uphill in energy. Okay. Now I could look at the other C beta, and what I see are 3 different groups. I see an ethyl, a methyl, and a hydride. So any of those groups could migrate over for the rearrangement. Now remember too, at this point right here, we could do an SN reaction from top or bottom, and we could lose a C beta H from any C beta carbon. So these are possible products if you were going to predict. So we said D is not reasonable. But what about if we took C, the ethyl group, with the electrons and migrated across? Okay, that will leave us a hole here. The carbocation carbon is secondary. We're coming from secondary. So that's certainly reasonable. But if we're predicting, we don't have to do that. Only if we had to explain something down here from the SN and E products that we got. Using this carbocation, would we have to show this? A second possibility from this carbon is migrate the methyl over with its electrons, and that again would leave us with a secondary carbocation right here. We could add from the top or the bottom, and so that would be reasonable, but we don't have to predict unless one of the products down here used this carbocation. The final possibility would be to move the hydride over to that carbon, and that would leave us with a tertiary carbocation. We're going to have to predict this one, okay, because this is the best carbocation. So again, we could add from the top or the bottom. Now if you look carefully, that wouldn't be different in this problem because this is an ethyl, and this is an ethyl. So this would be an achiral center. And so top or bottom attack would be equal. And then also I'd have to consider looking at all the C betas. So I have two C beta H's here. They would be different in the sense of E and Z. But they would be equivalent to these in the sense of E and Z. I could lose a hydrogen here and just get a geminal alkene. Okay. So I'm not showing all those products, but those are the SN1 E1 products that you could predict. Now, how does this rearrangement occur? Okay, so we showed the leaving group leave, bromide leaves, so we have our carbocation. If the hydride migrates over, the hydride doesn't pop off as an H minus and then pop back on. Okay, it's too unstable. So what happens is this orbital right here pulls the electrons towards itself, and it kind of bridges those two in the middle. And then whichever one is more stable without the electrons, that's the one that's going to end up with no electrons. So in this case, the tertiary would be better than the secondary, and so the hydride's going to move over here, and we'll end up with this tertiary carbocation. Then we would add from the top or the bottom. Again, in this case, they're the same. Or lose a C beta H. All right? So in following the energy picture of this, we had to go pretty high uphill in energy to get to the secondary, but possible. The secondary rearranges to a lower energy, tertiary, so that's good. And then the tertiary does an SN1 or E1. In our course, remember, SN1 is the winner over E1, but all are possible if you're going to predict all the products. So in this problem, we could either have a hydride shift or an alkyl shift. We didn't have an alkyl shift because we went straight to the tertiary carbocation with the hydride shift. Okay, so in our course, rearrangements always occur 1-2, from a beta carbon to an alpha carbon. In reality, that's not always true, but that's in our course, that's the way it will always be. So we could have again, if you predict, you have to show a secondary going to a tertiary, and you might have to show a tertiary going to a tertiary. Okay, that's predicting. But if you have to explain, you might have to also show a secondary going to a secondary carbocation rearrangement. Okay, so here's a little problem to test it out. Here I'm saying predict. So remember, on predict, you only have to go to a better carbocation if it's secondary, and then you have to be concerned about tertiaries and tertiaries because they're the most stable and equal in energy. So I look at the conditions, SN1, E1 conditions. Bromide has to leave on its own, so we show that. That's going to make a carbocation here. This is a secondary carbocation. If I tried to migrate from the methyl, that would be a primary. That's no good. If I came over here and tried to migrate a hydride, that would be a secondary. That's certainly okay, but we don't have to predict secondary to secondary. So we would just stop here. We would do say the SN1, E1. In this case, we're saying SN1 is the winner. So we could add from the top or we could add from the bottom. They would be different here because notice I have this big old group. I have a methyl, I have a hydrogen, I have the oxygen. That would be a chiral center. So rather than write that out with the dashes and wedges, I just wrote a wiggly little line which indicates both stereochemistries are possible here. I still have a problem because when the water added, it now has 3 bonds. So I have to take off a proton with another water molecule to get to the product that we have up here that we're predicting. So you'll notice water acted as a nucleophile here and water acted as a base here. Both things that are possible. This is a different problem now, because now we're saying it looks sort of the same, but now I draw a molecule over here and I say, explain that. How did we get here? Well, right away I see the bromine's on the 2nd carbon from the end here, but it's on the 4th carbon from the end here. Wherever this oxygen is, that must have been a carbocation to accept those electrons. So I must have done rearrangement. Okay, so let's see how we can do that. Neutral conditions, so we say SN1, E1, first step is the leaving group leaves. Before I move on, remember, to explain, I might have to show secondary going to secondary. Okay, so I show the leaving group leave. I make a carbocation, but it's not at the spot where I need down here, so I'm going to have to move a hydride over. Now, is that reasonable? Well, I'm at a secondary. If I move that over, it's at a secondary. So that is reasonable. If I move the hydride over again to get it where I need it, this is better than reasonable. This is really good, because now I have a tertiary carbocation. So this is going to be very favored. Water adds from the top or the bottom. In this case, it would be chiral because I have a methyl, an ethyl, and a propyl in the oxygen. I'm not done because the water has an extra bond now, and so I'd have to take off a proton with another water molecule as a base to show the actual product that we have to explain. Okay, now I'm going through these pretty fast, and what would be really good for you is to start back where I don't have any of the explanation shown, work it through yourself, and then double check your work with what we have on this slide. Here's another problem, another example. And so what is this? Is this a predict or an explain? Okay. If I had nothing shown over here, that would be a predict. And that would be an easy problem, easier problem. But if I say explain, we have to come up with this result in the end. What I see is the bromines on the second carbon from the end. And over here I see the oxygens on the fourth carbon from that end. And so this must be the carbon that was the carbocation. And that must mean I have to rearrange to get to this position here. Neutral water, SN1 E1 reaction conditions. First step is always make the carbocation. Okay, so let's show that. So here's our carbocation. I can't rearrange from the methyl because that would be a primary carbocation. But I could add a nucleophile here or lose an adjacent H, and so those are reasonable predictions if we're just predicting. But in this case, if I look over here, I have a hydride that could migrate over. That would give us a tertiary carbocation, and that's really good, so we'll do that. So now I have a tertiary carbocation. I'm still not where I need to be. I need to get this hydride to migrate over too. At this carbocation, this one right here, I could add a nucleophile or lose a beta H. So that would be more products that are possible if we were predicting. I could move this hydride over, and that would give me a tertiary carbocation as well. So you might say, well, this is tertiary and this is tertiary. Well, we said that's okay. You can use that to predict or explain. But in this case, it's even better because this tertiary carbocation has an adjacent pi system. So if I move the electrons over, the positive charge goes into the ring at this spot here. Then I can move the electrons over again. It goes into this position here. And then I can move the electrons over, it goes to this position here. So not only is this tertiary, but I put the positive charge at 4 different carbons. So this is really good. Also, that's the carbon I need to get the water to attack so that I can get the OH up here. So here I would attack with the water. That would come in from the top or the bottom. It's going to be a chiral center, which I didn't show. I should have a wiggly line here. And then we have to pick off that extra proton using water as a base instead of a nucleophile, and we get to the result that we need to get to. Okay? So that would be a chiral center. So we're just showing the SN1 product. If we had to show every product, we might have to show some elimination products, E1. But that's not what the problem said. It just said explain this. So here's another explain problem. Okay, it looks kind of simple, but kind of different than what we've seen. So I see the water here, so I'm thinking SN1 E1. I come over and look at this, I'm thinking the bromo part is a tertiary. So tertiary is good. I should be able to have that leave and make a carbocation here. If that were to happen, I would have 2 methyls on this carbon. But when I look over here, I have 3 methyls on this carbon. So how could that happen? Well, I had 2 methyls here. Now I only have 1. So it looks like one of the methyls here must have moved over. So let's try that out. Okay, the leaving group leaves. I have a carbocation. So now I'm thinking one of these methyls moves over. Okay. Now I have a tertiary carbocation. Oh, not tertiary. I have a new carbocation from what was a tertiary carbocation. So you might at first look at that and say, well, there's only 2 carbons here. That's kind of secondary. But I do have an oxygen with lone pairs. So the lone pairs can donate in and make a resonance structure, which has an extra bond and full octets. And remember, we said that was the best resonance structure. So the thing that helps drive this is this extra resonance structure. Now I'm still not done. If I look up here, I don't have this hydrogen here. So I need a base to take this off. Since we're in water, water will be our base. Okay. So we use water to take off that proton, and that gives us the final result we need up here. So again, set this up without any details, work your way through it, and then double check with the answer that's shown here. Okay, that's what you need to do. You need to practice that until you can do that just out of your own head. So this is kind of a summary slide of all the stuff we've been talking about so far. You'll see up at the top I have all these different nucleophiles. Okay, some of them are also bases, but a lot of them, we're mainly interested in them as nucleophiles. So if I look at the methyl, what do I got? I got a methyl, a primary, a secondary, and tertiary. So methyl is super easy because every single one of these guys is an SN2 reaction. Okay, that's the only thing that the methyl does. I need a minus charge, and it does not do E2, only SN2. It will not react by SN1 or E1 because we cannot make a methyl carbocation. So this is pretty easy. Now if I come down to the primary bromoalkane, this is pretty easy too, because SN2 wins everywhere except T-butoxide up here. And that's because this is big and bulky and basic, and it does E2 over SN2. Okay, so this is the only place where we can get an E2 at a primary bromoalkane. So it's an exception, but it's an important exception because everything else is going to be SN2. When we get to the secondary bromoalkane, things get more complicated. Okay, now not everything is SN2. So what happens is, as these get more basic, E2 starts to be favored. And so E2 is favored over SN2. Really, for T-butoxide, it would only be E2. But the ones that are less basic, that are more stable anions, they do SN2 over E2. Okay, so that's still the same. SN2 wins, except on this terminal acetylide. They are too basic. And so at secondary, the E2 wins over SN2, which is too bad because that triple bond could really be used a lot of different ways, but we can't do that at a secondary center. Okay, here's an enolate. Enolates are very important in organic and biochemistry, and so we can do SN2 here over E2. Remember, this is a ketone enolate, but we also have ester enolates and nitrile enolates. So those are also very useful, and we can make both those kinds of compounds from our starting materials. And then I have the aluminum deuteride here, which we use. We also have sodium borohydride, borodeuteride, but I'm just showing this one here, which is our main one. So we're going to say that's SN2 also. And then we come to the tertiary bromoalkanes, and this again is pretty easy because this is too sterically hindered for SN2. So everything is E2. Alright, so that's kind of simple, but I shouldn't say it's easy, because remember, each C beta could be different. So I could have 3 different C betas, and on one C beta, I could get E or Z. So this could be actually sort of complicated for all the possible products. Okay, so down here, if I had a dibromo, I could do a double elimination. This time we would use sodium amides or sodium amides to do the double elimination. We can't stop, after we make the alkyne, we can't stop taking off that proton. So we have to do a final workup step to get back the alkane, or we have the possibility of bringing in a methyl or a primary bromoalkane and doing an SN2 to make a bigger alkyne. So that would be kind of useful. Remember, that's one of our nucleophiles that we have up here, and this was a way we could make it. For the SN1 E1 neutral conditions, here's a methyl, primary, secondary, tertiary. And so this would either be neutral water or neutral alcohol, methanol, ethanol, something like that. And what we saw was to make a methyl carbocation or to make a primary carbocation was not possible. So this is really easy. No reaction and no reaction. If I get to secondary, then I can do make a carbocation, attack from top or bottom, lose C beta H's. In our course, we're going to say SN1 is always the winner. Okay, if it's at secondary or tertiary, SN1 is always going to be the winner. We only have one place where E1 is the winner, and that is if we have an alcohol and sulfuric acid with heat, which we'll study at the very end. Okay, so let's take a look at another problem here. We have predict the major and minor products in each part. So I have 2R bromo, 3R methyl, pentane. You'd have to write 5 carbons in a row. At the second one you put a bromine. At the third one you put a methyl. And then you try and arrange the stereochemistry in the right way. Okay, so I have that down here. you can double check. 1 bromine, 2 this side, 3. So this one rotates right, that would be 2R bromo. If I come over and look at this center, the carbon with the bromine, ethyl over methyl, again I'm going clockwise, so that would be R. So this is 2R, 3R. Now I have two sets of conditions here. So if I look at the top set of conditions, I see the negative charge on the nucleophile base. So I know this is going to be SN2E2. That requires very specific results, reactions for the reactions here. On this one I have neutral, so I know the first step is going to be make the carbocation, and then I got all kinds of possibilities, including rearrangement. So let's take a look at the products. We'll look at each step of the products in just a little bit. So up here, I can lose a proton from the right side over here. That would be an E2. They're all equivalent, so it makes no difference which one, but it has to be anti-C beta H. On this side here, I do have a hydrogen. So the only way I'm going to lose this is with the anti-conformation, and so that would lead to something like this. Notice the two methyls are together. Okay, if I used a different configuration here, I would get a different result. In this case, I got the big group here and the big group here. This would be E. Now, if I lose this group here and make a carbocation, oh boy, there's a lot of possibilities now. I could make the same kinds of alkenes up here, but E and Z. I could get the top and bottom attack from the nucleophile and lose a proton. But also, if I move a hydride over to that site, I get a tertiary carbocation, and then I can start all over. So now the water could add from the top or the bottom. This turns up being achiral because now I have an ethyl on both sides. But I also have a new possibility for E1 because I can lose a hydrogen from up here, in addition to losing it between these two. So you can see the E1, SN1, E1 possibilities are a lot more than the E2, SN2 possibilities. Okay, so first you want to look at the reaction conditions: strong, weak. You want to look at the C alpha carbon, see what kind it is, whether the reaction is possible. And you also want to look at the C beta for any elimination possibilities or rearrangement possibilities. Okay, how many C betas are there? Are they different or are they equivalent? You got to make those decisions. So our possible mechanisms: if it's SN2, we only do backside attack at C alpha, inversion of configuration. If it's E2, we only do anti-C beta H C alpha X, and that will lead to a specific E or Z result. If it's SN1, we get an attack from top and bottom. If it's chiral, it could be R and S. E1 could be from either side with any C beta H, and so that means a lot of E and Z possibilities. Okay, so here's the SN2 possibility right here. We come in from the back side, and so now we get the dash instead of the wedge. So instead of being 2R, 3R, now we're 2S, 3R. 3 stays the same, but the S inverts. If I want to look at the E2, this has to be anti, so this is back, this is in front. And if I do that, then the two methyls are together. Okay? And that's the only result we would get for this E2. If I look on the other side, this is pretty easy because all three are the same. So if I do the anti-elimination, I get the mono-substituted alkene. And so these are all the two reactions, SN2 and E2. Now what if I had started with different configurations? Then it's very possible I would get different results. So here I have 2S and 3S, so you can see what the results are here. Here I have a 2S and 3R, so that's going to be a little bit different yet. So 3 would be the same, but notice I inverted the bromine at the start, so that would be S. So then I would get a different result down here. And also I get a different E2 result between these two carbons right here. Okay, what if I had these conditions? These conditions are SN1 conditions. So I don't do anything with the alcohol. I just ionize the bromide off and I have a carbocation. So now I'd have to look at SN1 and E1 possibilities here. Okay, but if I migrate the hydride over, I would have a tertiary. That's going to be even better. So then I would have to look at the SN1 and E1 possibilities here. So you can see this is double the work at least, because now I got two different carbocations to analyze. So let's take a look at the first one. So at the first one, I just show the nucleophile attacking here. That could be top or bottom. So if I look it over at the results here, the SN1 results, I can see that those are going to be different because this is a chiral center. All right? So I would get two possible SN1 products from the first carbocation. And then if I look at all the possibilities for losing the hydrogen on this side, I would get E or Z, both, because that hydrogen could be lost from either side. And I also get the hydrogen loss from the methyl side over here. And so you can see just this first carbocation leads to all these different possibilities. Now what happens if we rearrange and make this guy? Okay. Oh, first off, just to point out, no chiral centers here, but these are diastereomers because this is E and this is Z. So those are diastereomers, but not chiral. In this molecule, in these molecules, I have a chiral center that inverted, but a chiral center that stayed the same. So these are going to be diastereomers. Okay, and I have two chiral centers that you can figure out the stereochemistry of. And then what about this guy? Okay, I can't have any E or Z because I got two hydrogens up here. But I do have a chiral center because now this branch is different than this branch. This is an ethynyl and this is an ethyl. So this would be a stereo center. What would it be? 1, 2, 3. So this should be R because the hydrogen's away. All right, now what about the rearrangement possibility here? So if I rearrange it over, and then I still have SN1 and E1. So if I come over here and look at the SN1, notice I have an ethyl and an ethyl. So this is no longer chiral. So I do not have to worry about R and S. I just have to show one product. If I do the elimination, I can lose the proton here. Either one, there's a CH2. Either one would give two different alkenes between these two. Okay, so that would be the E and the Z. We had sort of that same result up here. And then I could also lose a proton up at the top here, which I could not do over here. Okay, so I couldn't lose that proton up here because the carbocation wasn't here. So that's a third possible alkene. Okay, so if we look at all the possible products from the SN1 and E1, it's a mess. All right, oops, let's go back here. We have 1, 2, 3 different types of SN1. These two guys right here are the same, so that's 1, 2, 3, 4. So 4 different possible alkenes. So quite a lot to explain everything. Okay, so now we're going to go a little bit farther than we've been doing. All we've been using so far is bromoalkanes for these reactions. But there's many other useful ones, and I'm going to look at 3 of them here. I did have 4 listed, 1, 2, 3, 4, but I'm going to leave 3 out, just for time purposes, and it solves a really important problem, but it's not going to be so important for us. We won't worry about it. Okay, so the first one up here is going to be to take an OH from an alcohol and make it into a bromoalkane. Now that might seem kind of silly to you because all we've been doing is taking a bromoalkane and making it into an alcohol. Like this is the only way we can make an alcohol. But in fact, there are many ways to make alcohols. So many that are coming. And that means if we could make alcohols into bromoalkanes, we could use all those ways to make alcohols to do this. And then we could use this for all sorts of things beyond what we've talked about so far. So what we're going to do is we're going to take HBr. Well, we know what HBr is. It's a super strong acid. And if we put HBr in water, 100% it ionizes. And so we're going to do that to the alcohol. Now another way we could do this is to use phosphorus tribromide, okay, and an alcohol. Now I have 3 bromines on the phosphorus, and so I can do this on 3 different alcohols to make the bromoalkane. So we'll take a look at this too. The nice thing is these reactions have a lot of similarities, and the reactions I'm showing here are really just a double SN2, and we're familiar with SN2, so these should be very understandable reactions. This one, it's important, but we won't show this one. And this is our only reaction where E1 is the winner. So we got to have one of those, and alcohols with sulfuric acid and heat will do E1, make alkenes. Okay, so we'll take a look at each of these. Now these reactions all have a lot of similarities, and that's what you want to try and focus on. Alright, so HBr is a super strong acid, so is HI, so is HCl, so is sulfuric acid. So we could use any of these, but remember we're just sticking with the bromoalkanes, so we'll use HBr, very, very strong acid. sulfuric acid we'll use in the E1 reaction, so we need that. All right. H3O plus is the strongest acid possible in water, but we're not going to worry about that. And then water is just our reference point right here. We don't consider water really to be an acid. It can be if we have a super base, but that's just for reference here. So this shows you the pKa's. They're all negative except, of course, for water. And the Ka's are very, very large except for water. All right. So now if we look at how these reactions occur, we're taking an alcohol and we're reacting it with HBr. Well, we expect that to protonate. If I protonate, I have a water molecule sitting here. That should be a very good leaving group because water molecules are real stable. I also made a bromide in the same mixture, which is a good nucleophile if I can push off the water. And if I do that, I take the OH and I make it into a Br. This is a great reaction because this will allow us to make a lot of bromoalkanes that otherwise would be difficult to make. All right. The water itself would protonate again, but we don't really care about that. That's just kind of a side product that we ignore. This is what we want. We want the bromoalkane. Now, I do not make an SN1 reaction. The bromide has to push off in an SN2 because remember, this is a methyl. We do not make methyl carbocations. Now, if I come down and did this with a primary, same idea. It's going to protonate essentially 100%. I have a very good water leaving group. I have a pretty good nucleophile that can push off the water, and that's going to give me the bromoalkane I wanted. The water does not leave on its own because this is a primary, so I cannot make a carbocation here, right? And that gives us primary bromoalkanes. So this is really, really useful. Let's look at secondary and tertiary. Now, if I had a secondary, same thing. I protonate the OH and I make a good leaving group, a good water leaving group. But notice this time, this is a secondary carbon. So as a secondary carbon, this is going to leave on its own. And so I'll have a carbocation sitting here. Now it's possible it could rearrange. This is secondary. I could go secondary up or secondary down. But if we're predicting, we don't do that. We just say secondary. I can't make a tertiary, so I'm not going to show anything else. The bromide can add from the top or the bottom, because remember SN1 is the major product. So if I add from the top or the bottom, would it be different? Well, it is different because I put this methyl over here as a marker on the top. If I didn't have this methyl here, adding from the top or the bottom would be identical. But with the methyl here, if I add from the top, it's going to be different than if I add from the bottom, because this is cis and this is trans. Now I do not have any chiral centers. Kind of looks like it because I drew in wedges and dashes, but in fact, the path around here is equal to the path around here. And so this is achiral, but they're still different stereoisomers, so these are diastereomers, okay, but no chirality. Now if I did something similar with a tertiary alcohol, so all I did was take this molecule and I put a methyl group here, so now this is tertiary. I'm still going to protonate just as we did in the previous three examples. I have a very good water leaving group. Carbocation forms even easier because it's tertiary. Bromide again can add from the top or can add from the bottom, and with the methyl marker out here, those are going to be different. So here I have the bromine and the methyl group on the top, and here I have the bromine and the methyl group opposite trans. So again, there's no chiral centers, but they are not the same. They are diastereomers. Okay, so this is our important reaction now. We take an alcohol, we add HBr, and we get a bromoalkane. Let's take a look at the phosphorus tribromide. We're going to use this for more than just the alcohols. We're also going to use this for carboxylic acids. Alright, so the phosphorus tribromide has three good leaving groups on phosphorus. So right away we can see the bromide leaving groups. Also, phosphorus and oxygen love each other. Okay, they make a very strong bond. So I can use the oxygen here to attack the phosphorus, join these guys up, which love to be bonded together. When you look at nature, phosphorus is always surrounded by oxygens. Push off the leaving group. Now when I do that, this whole thing becomes a good leaving group. Okay, it becomes a neutral molecule leaving group. I have bromide in there, and just as above where I pushed off water, now I can push off this sort of a phosphoric acid. So I push that off. Notice there's still two bromines here, and I can do this 2 more times with 2 more alcohols. And I made my bromoalkane. I did not show an SN1. I did not make a carbocation because this is a methyl group. and we do not make methyl carbocations. Okay? So here again, we can make bromoalkanes from alcohols. If I use a primary, everything looks the same. Oxygen attacks the phosphorus, push off the bromide. Very good leaving group, but it's at primary, so I have to use SN2 to push that off. Okay, and now I have a bromoalkane. 2 more bromines on the phosphorus can react 2 more times. All right. So now let's go to secondary and tertiary. So just as before, I can attack the phosphorus, push off the bromide. I have a bromide, a good bromide nucleophile. In this case, since it's secondary, this group can leave on its own. So then we form it over here. And then the bromide can come in from the top or the bottom, just as we showed with the HBr. And we get diastereomers. Okay? So cis and trans. If I do that at the tertiary, so I brought a methyl here, and now it's tertiary. Same thing, we attack, push off the bromide. We have a very good leaving group. Tertiary is even better, so it leaves and makes a tertiary carbocation. We can attack from the top or the bottom, and now we get a bromine. Again, these are going to be diastereomers with this methyl marker out here. So as far as we're concerned, these 2 reactions are pretty equivalent to each other. You could use HBr if you want, or you can use phosphorus tribromide if you want. Okay, either one in terms of taking an alcohol and making it into a bromoalkane. Now the reason that I showed the phosphorus tribromide is because of this reaction here. This is a super important reaction for us because it's going to take our carboxylic acids, and right now I only give you one. I only give you ethanoic acid or acetic acid. But after topic 10, we'll be able to make many carboxylic acids. And we'll be able to make all of those carboxylic acids into acid chlorides. And if we can make them into acid chlorides, then we can take all those acid chlorides and we can make esters, we can make thioesters, we can make amides, and we can make anhydrides. So these are a lot of our other functional groups that we can make that we otherwise could not do. So this is a super important reaction for you. Now it can actually make other things too, but we're leaving those out. It can make aldehydes, it can make ketones, and various things like that. So how does this work? Well, if you look up above what we just did, we used the oxygen to attack the phosphorus and push off a bromide. So let's come back down. We're going to use the oxygen to push off a chloride, attack the phosphorus, push off a chloride. I don't use this oxygen down here, because if I use the top oxygen, then I get resonance structures. Okay, and these are going to be better to use the carbonyl one. And then the chloride leaves off. Now you might say, why didn't I use a bromide? Well, the reason is because if we use a bromide, then the acid bromides are a lot less stable. They don't tend to stick around very well. So we're going to use the acid chloride because they're more stable. And you can actually buy some of these in bottles, and they'll stick around for a while. Okay, so if I attack, I have the carbonyl up here with the plus charge. I could borrow these electrons in, put the plus charge on the other oxygen. Right? So I have this kind of a positive group in the middle with the chloride. The chloride can come up and attack, give the electrons back to the oxygen. Okay, some base out in solution can pick off this proton, remake a double bond O, and kick off this good leaving group right here, okay, which is what I'm showing right here. So this would be from another molecule. Kick off that leaving group, and notice what we have. We have this acid chloride. All right, so this is kind of a new mechanism. It's not totally new. It's sort of related to ones we've seen, but it's one where you probably want to practice it a little bit. Remember, every time you practice these arrow pushing mechanisms, you get better at understanding what's going on. Now this could actually react 2 more times because I got 2 more chlorides, but we don't show that. This is what we want right here. So now how is this going to give us all these other products? So let's take a look at that. So I have here all of the steps without the details. On the next slide I have all the details. So you want to try to think your way through this. When you look over here, what happened? You want to try and match up what was it here that reacted to get over here. And so what I see is the acid seems to have joined up with the carbonyl. That's the way we always do it. So it seems like I've joined this up right here and pushed these up. It looks like I wrote a resonance structure here, right here. Then it looks like I pushed these electrons back and kicked off the chloride. And then it looks like I picked off the proton with the chloride to make an anhydride. So notice I have an acid chloride that I made from an acid, and I have an acid that I joined together to make an anhydride. So again, right now we only have ethanoic acid or acetic acid. So I would have to use ethanoic acid to make this, and I would have to react it with ethanoic acid here, and that would give me ethanoic anhydride, or more commonly called acetic anhydride. But like I said, we'll be able to make many, many carboxylic acids pretty soon. So we can make all kinds of anhydrides. If I come down here, I could use the sulfur as the nucleophile. I'll let you trace through the same steps. We push up. Okay, so then I push back down and kick off the chloride. And so I could use either of these guys as a base. I used another sulfur as a base here, like we did with the water. And that would give us the thioester. Do the same thing, almost exactly the same. Instead of sulfur, we're using oxygen. Get to an ester. Remember, we have another way of making esters. We can make esters from SN2 reactions at bromoalkanes, where this is methyl primary or secondary. So now here's, we're getting into more than one way of making a functional group. And there's other ways too. Here, if I use the nitrogen instead, remember we can make a primary amine. We use the azide, followed by aluminum hydride, and then a workup. So we can make the primary nitrogen, and pretty soon we'll be able to make secondary nitrogens and tertiary amines. So we'll be able to make, this is a primary amine, we'll be able to make secondary and tertiary amines too. But now we're going to use this to make an amide. So we don't have a way of making amides, but we do now. We don't have a way of making thioesters, but we do now. We didn't have a way of making anhydrides, but we do now. We had a way of making esters, but now we got another way, and they all come from the acid chloride. Okay, so here's all your steps. If you're going to practice this, you can use the template here to try and work through all the steps, all the details. Notice I didn't have a minus charge on the chloride here. I didn't have a minus charge on the oxygen, and things like that. I don't have a plus charge on the sulfur. I don't have a plus charge on the oxygen. I don't have a plus charge on the nitrogen. So you'd have to put in those details. But hopefully all those details are here. So you can see the minus charges, the minus charge on the chloride, the plus charge here, and so forth, with all the arrow pushing. These are a lot of repetitive arrows. Okay, they're not exactly the same, but they're very similar. And so practice, practice, practice on those. And you will get pretty good, and you will start to think organic chemistry is not that hard. Okay, our last reaction we're going to look at to finish off this topic is to take alcohols again. But this time we're going to react them with sulfuric acid. So sulfuric acid is a really heavy acid that has a very high boiling point. It's a really powerful acid when it's concentrated. And so we're going to heat this up. Okay, what that's going to do is what you would expect. Sulfuric acid protonates water. Sulfuric acid protonates our alcohol. We'll look at the carbon here, secondary carbon. We think that could easily make a carbocation. And if it makes a carbocation, we could add a nucleophile, or we can lose a beta H. Now, just adding a nucleophile would normally be the preferred reaction. But notice what we have over here, heat. So we're going to cook this guy up. If we look at the alcohol, it boils at 161. That's pretty high. So we could heat this up to, say, 100 degrees, and this guy is just going to stick around. But if we look over here at the alkene, I've lost that OH, and so now it boils at a very relatively low temperature of 83. And so if I'm cooking this up at 100 degrees, this is going to distill out. And so the alkene, the E1 product, distills away. The reaction keeps trying to equilibrate and make more of it, which distills away. And so we kind of trick the reaction to come over to the elimination side because of the boiling points here. And so we get E1 product instead of SN1. Okay, so this is a way of making alkenes. Now we have other ways. Remember, we had the T-butoxide with the bromoalkanes for E2, and we also had E1, but we said none of those outcompeted the SN1, so that wouldn't really be good for us. So let's take a look at this reaction right here. We're going to combine a couple things together here. Okay, I have an alcohol, sulfuric acid, and heat. I think I'm going to protonate this guy. Okay, so I protonate, and that would make a good leaving group, and I'd have a carbocation. Since we're heating it up, we expect alkenes. Now look at all the possible alkenes. How did this happen? Okay, so you can see I had two methyls up here, which I do here, but that's the only place. Every place else I have methyls on different carbons. This must involve a rearrangement. Okay, so if we protonate, make the good leaving group, and it leaves carbocation, we could do an E1 reaction here. So if I do the E1, I only have this carbon with C beta H, no C beta H up here, so I can only make this alkene. Okay, but I have a methyl up here that could migrate down, and that would give us a tertiary carbocation. Okay, coming from a secondary, this is going to be a good reaction. Highly competitive. Now, if I have this carbocation, I'd have to look at how many C betas I got. I got a C beta CH2. I got a C beta CH3. I got a C beta, just a single H. So I could lose an H from all of those guys, and it's going to be different. If I lose it from up here, there's still one H here, I get this tri-substituted alkene. If I lose it from the methyl out here, I get this geminal di-substituted alkene. And if I lose it from down here, I get the tetra-substituted alkene. Tetra-substituted, we said, is the most stable. Okay, so we would expect this to be the major product. But look at all the possible alkenes that we have to consider. Two different carbocations and all the possible C betas that we have to look at. This would be the best alkene. This would be second. And these two would be similar. Geminal and cis are about the same. So I think that's just about it for this topic. This particular third lecture has a lot of new stuff, a lot of important stuff. So you might want to look at this more than once and maybe do a little practice as you go through the slides with pencil and paper. That would help you out a lot. Okay, so we'll be starting on chapter 10 pretty soon, which will be free radical chemistry. Okay, this is our only E1, useful E1 reaction.